in the Sarajevo project. Mariusz, I give you the floor.
Yeah, good morning. Can you hear me? Can you see the slides?
Loud and clear.
All right. Very good. So thank you, Nadia, for presenting the ion sources, because this is the essential component of the project that we are working on now for Sarajevo University. I start with a little history, first the motivation of the project. So there is a quite limited experience in accelerators in Southeast Europe region. Limited means there is some, of course, and there are, for instance, electrostatic machines in Ruđer Bošković Institute, and I think Miloš will talk about it. Then there is a cyclotron for radioisotope production in Macedonia, and I don't know if somebody is from Macedonia here, but actually, first time I found it on the internet a few days ago, and I never heard about this before. It would be interesting to know a little bit more. And then there are two very, very established known companies, both in Slovenia, which actually produce accelerator components for all the world. So ITEH, I start with the second one. ITEH is producing electronics, readout electronics, digitizers for instrumentation applications really all around the world. You find that the devices at CERN, in JPARC, in Japan, in US. And Cozy Lab is even a bigger company, and they actually focus on control software. And both companies are really worldwide recognized. So we think that surely new accelerators will appear in the region, whether this is the CEAST project or no, that there will be some proton devices sooner or later, because yeah, this is how it happens everywhere around the world. The new medical centers appear, or accelerators for applications in industry or radioisotope production, they are installed in more and more places. Therefore, there is a certain need for additional experience in accelerator techniques, in vacuum, in RF systems, in beam measurements, ion sources. And this is how the idea of accelerator laboratory at the University of Sarajevo came into life. The story, well, I joined somewhere in June 2020, so what happened before is a little bit not clear to me. But somewhere at the beginning of 2020, Jota Foka, who is one of the organizers of the school, the main organizer, and Eddie Offerman, they met and they discussed ways to support and develop University of Sarajevo. And I think around May, there was the idea to establish the new accelerator laboratory. And in June, I mostly written the first proposal, which foresee the ECR ion source in the first phase and RFQ in the second phase. The main application at the time, we thought it should be basically the laboratory, which would do research on accelerators. We thought about extraction system optimization, which actually one of the students is now kind of working on. And we thought about it also as the future CEAST hub. But all right, then in October last year, two students, Fehima and Benjamin, joined the project. You heard already the presentation of Benjamin on Tuesday, and Fehima will present in the afternoon what she did. And they are basically doing, well, at the time, Benjamin was doing kind of research on the market, where can we get, what kind of ion sources. It was really interesting. We actually met online multiple companies, I think 4 companies. We learned really a lot about what is available. And Fehima was looking at the applications of light ions. This is also very interesting. And actually, we learned that there is this huge experience in Ruđer Bošković Institute, which is right in the region. And we started to ask questions to Milko, and I think in the next lecture you will see a little bit more about it. In November, at the University of Sarajevo, a task force was established to follow up the project and coordinate it, and to find the laboratory, to find out if it's good enough, if it has enough shielding, enough media, cooling water, electricity, all these things. And in January, we concluded discussions with experts at CERN to establish the basic ion source specification. Because there were various ideas. At some point we thought about super nanogun source, then we thought about the proton source. Finally, we came to a conclusion, which I will present in the next slides. Then in April, we started to prepare technical specification for phase one. And it's still kind of ongoing because, yeah, recently there is really a lot of work, but I think we will conclude it by the summer. And also what is very interesting is that there is a collaboration agreement that was signed, I think in April, between CERN, Sarajevo University and COSILAB. And it is not only about the providing the control system for the new facility, but also to transfer knowledge, to organize courses, all these things which COSILAB has a lot of experience in controlling the machine. And the control system is definitely one of the most important things in the project like that. All right, so this is the baseline proposal. We actually don't have technical drawings of what we want to do because it's a little bit too early, but we are heavily inspired by what Heidelberg has, Heidelberg Ion Therapy Center. They have a test bench. And I don't know if other places also have test benches like that. But yeah, basically they have a test bench and we want to do very similar thing. Here is the ion source itself. Here is the analyzing magnet. Then we need to have some diagnostics. Then we need optics in order to prepare the beam to match it to the RFQ accelerator. So here is the three optical elements, which in this case are electrostatic quadrupoles. And here is the second diagnostic chamber. So we want to measure beam properties here after the analyzing magnet and after the quadrupole triplet here in order to make sure that we fit to the RFQ. And then after RFQ, there are additional components. Now we are going to change, of course, quite a few things. So for instance, we are discussing a lot what kind of ion source we should have. We are discussing whether we do need analyzing magnet at the beginning, because it's a quite expensive piece of equipment. We are still discussing what kind of diagnostic we need in the diagnostic chamber and what kind of optics we need. So this is still ongoing. The point is we buy it in the industry, so we cannot really say we want exactly this and that device. We have to specify what beam parameters we expect as a result. Therefore, the process is not only on our side. We are not building it; we are buying it. So it's a collaboration with industry, and they can propose solutions which maybe we didn't think about at the beginning, but which fulfill our requirements. All right. So there are these two phases. Basically, they are split here, somewhere here. The phase one is the ion source and the low energy beam transfer, and the phase two is the RFQ. For the first phase, we have, yeah, I think we've done quite a lot of work, and we very well decided what should be done. For the second phase, we are still in a kind of investigation phase because there is a lot of developments on the RFQ, as I will tell you in a moment. All right, so the phase one, the ion source. We decided to go for the ion source, which is able to produce 100 microamps of helium-2 plus beam. For example, nanogun from Pantechnik. This is, yeah, I couldn't do really the advertisement for particular company here, but nanogun is, there are not very many companies which produce ion sources, and nanogun is really a good product, and we are thinking about it. However, of course, our procedure is open to any company. The nanogun is significantly smaller than super nanogun. It's easier to handle, emits less radiation, a little bit cheaper. So it will not be useful for cyst because it does not produce enough carbon beam, but maybe it can be a secondary source for helium or for protons. It can still produce measurable intensity of carbon beams. So in case we want to test for instance, our instrumentation with carbon beams, we can still do it with nanogun. Why we went to nanogun instead of super nanogun? Well, mainly because as Fehima will explain you in the afternoon, our laboratory developed. It's not going to be just accelerator laboratory, to develop accelerator techniques for CIST, but it is going to be also a laboratory where actually some research, material research will be done. And this material research is done with two methods, PIXI and RBS. And therefore, we do need protons and helium and actually not so much carbon. And the simulations of low energy transport is done by Benjamin. Okay, this is the specification of nanogun. So basically what you see in this table is the ion and the charge state. So you see nanogun is able to produce protons at 1 milliamp. So the units are microamps. It's not written here, I'm sorry. Helium 1 plus in 100, also in 1 milliamp and 100 microamps in helium 2 plus. Then carbon is not written here, but it still is able to produce some single microamps of carbon 4 plus. If we want to test one day, this kind of a beam. All right, the timeline, the time is always getting short and short. If I show you the timeline of the project that I thought in November, that you would be surprised how much delay we have. So, but now we think that in June, maybe July, we will make the order to the industry. Then it takes around 1 year to produce the components, the whole device for phase 1. Huh? And so it should be delivered to CERN actually initially somewhere in summer next year. And there is a first phase of tests that will be done at CERN. And actually why we do this at CERN first is because CERN is now building a new RFQ, 750 megahertz RFQ for charge to mass ratio 1/2. I think it's not very well written in my points here. And this RFQ is a potential candidate for our phase 2. So it's really interesting that we could already test it with the prototype RFQ at CERN. At the end of 2022, we think we will have a decision concerning which RFQ we will actually order for phase 2. And in January 2023, the source will move to Sarajevo. And somewhere in May 2023, we expect that the phase 1 setup, so that the first part will be commissioned at Sarajevo University. Then we will go on with phase 2, so the RFQ ordering and production will take time. I don't include this phase 2 timeline here. All right, what is interesting is that because there are these two companies which are in the region and they would like to participate in the project, and of course we would like them to participate in the project, then the control system, which normally when you order such a device together with elements is done by the manufacturer. In our case, the COSY Lab will do it. Of course, in a collaboration partnership with the company which will win the contract. The COSY Lab control system will be used from the beginning. So already at the test at CERN, we discussed, we were thinking about using CERN control system, but actually we think it's actually better to use already COSY Lab control system. For the instrumentation, we are also not going to order it immediately from the company that is providing the ion source. We think we will, for test at CERN, we will have CERN instrumentation, at CERN with these large structures of multiple accelerators. There is a lot of instruments which can be borrowed for several months. The same is for the analyzing magnet. We will not order analyzing magnet at the beginning. So those two elements will be acquired separately for the university later. And the instrumentation we would like to do with HITRIplus company. We are discussing with them. Now it's not so easy because they are mostly focused on the electronics and we still need some hardware. So we need to find a good arrangement for this. All right, so the RFQ, the second phase, I think it was quite nicely discussed by Giovanni on Wednesday. It's a very particular device. It has these 4 electrodes which has a special modulation, and the special modulation provides so the electrodes by themselves they would provide focusing, but because of this modulation you get basically also acceleration. It's not very efficient acceleration. So you normally don't want to have very long RFQs, especially that they are quite expensive. However, for this region, energy range between ion source and a few MeV, RFQ is a very good accelerator. Of course, we have a lot of discussions with Milko, and Milko maybe will be commenting about that. It's not really a perfect accelerator for ion beam analysis methods. But because we are at the same time trying to be accelerator laboratory and the hub for CIST project, we decided to go this way. Yeah, we decided to go this way. All right, I think I said everything here. I think this is also something that is quite fascinating, and we are going to participate a little bit in this development of RFQ at CERN. As a group, and it's really fascinating how these devices work. All right, so the principal requirement for ion beam analysis is that the energy of protons should be around 2 MeV and helium 1 MeV per mass unit. And the big question is the duty factor for the beam, and this is what we discussed quite a lot with Milko, and probably he will comment, saying that RFQ is not such a good idea, because the main difference between electrostatic accelerator and RFQ accelerator is that electrostatic accelerator provides you rather small intensity beam, but duty factor 100%, and so you have it all the time. And the momentum spread is order of magnitude better than for RFQ acceleration. However, it's a big device and not very useful as an injector for CIST. So we have to compromise somewhere. As I said, that the technology is not yet decided. The good candidate is this new, completely new 750 megahertz RFQ, which is now being developed at CERN. There is actually one which is already done for protons, but protons is charge to mass ratio 1, and now another one has to be done for charge to mass ratio half. There is another idea of using RFQ developed by Bevatech company in Frankfurt, Germany, which works at 325 megahertz, which is maybe a little bit safer frequency because the manufacturing tolerances are better. We will have to see at some point which way we go. And this is the final layout. So this is the room that was given to us by UNSA. You see, this is not to scale, unfortunately. It's not the CAD drawing, it's a Madix drawing. So it's the elements, they don't have a width, but they have the right length. And there is the ion source analyzing magnet, the optical elements, in this case quadrupoles. Here is a branch for low energy experiments. Here is the RFQ. We think it should be this 2 MeV RFQ. Here are additional optical elements, and the blue are dipoles and the red ones are quadrupoles. And we foresee for the moment, so what you've seen, that the Heidelberg test bench ends here, but of course we continue, and we will have 2 experimental stations here. And then we have some storage room because we always need a lot of equipment together with the machine, and the control room. We also look at together with Harris, who will present later, at the radiation protection issues, and I think we have it under control. Okay, so I come to my conclusions. We think that Sarajevo Linac will provide university with interesting research opportunities, and there are already some researchers which express the interest in using the beams. It will definitely participate in capacity building in the region. It may become an accelerator technology hub for CIST. So CIST is going to work this way, that there will be a place where the accelerator is, the actual place, but there will be several places around which will closely collaborate. And for instance, we think that testing of the ion sources could be done at the Sarajevo University before moving it to the main machine. Project is already funded. We are still working on the details, how we can use this money in the most efficient way. There is university position associated with the project, and I think recruitment is either still ongoing or just finished. Laboratory space is designated, and we expect BIM in Sarajevo in 2023. So thank you very much.
Thank you, Mariusz, for that very interesting talk. Can you unshare your screen?
All right, so there are a few questions. The first question, could you tell me about electrostatic accelerators you mentioned at the beginning of your presentation, such as energy, ion species, and beam current? So there is, I think there is an expert speaking right after me, and he will explain everything. Is there a good practice using a Linac without TPS at the center? Oh, what is TPS? Therapy planning system, right? Treatment
Planning.
Without treatment planning system at the center. Yeah, well, I mean, first of all, our Linac is not going to be used for therapy. I think it's now you are probably referring to Linacs that are used for gamma ray therapy, right? I don't know. I cannot really answer this question, but I wanted to make clear that the Linac at Sarajevo University is not going to be used for therapy. The energy is way too small. We are thinking about someday in the future maybe to use it for radioisotope production, but not for direct therapy. Could you comment more on connection of this project to CIST project? Yeah, well, I think these are all a little bit political aspects. I think that's basically what I said. It may become a CIST hub for accelerators. I think at the moment, this is the project that actually is funded. CIST is not funded. Well, there is some funding, of course, but the final construction is not funded. So it's difficult to say more than what I said. Is RFQ a medical accelerator? Yeah, the RFQ by itself does not provide enough energy. RFQ accelerates to 1-2 MeV per nucleon. Well, some are accelerating to 5 MeV, but this is still way too low. We need this 60 MeV, right? So you need a Linac afterwards, or maybe sometimes we are thinking we don't need additional Linac. We inject directly from RFQ to the synchrotron. There is also idea like that, but we do need another machine after RFQ. RFQ is good for this low energy part, but afterwards it's really not efficient. For higher energies, it does not provide efficient acceleration. Is RFQ a linear accelerator? It's a kind of linear accelerator, yes. They are not bent for the moment. But it's not the whole story, right? After RFQ, usually we have drift tube Linac. Why is quadruple triplet used instead of just single, quadruple, or two? This is a very interesting question, actually. I don't know if you remember the ellipses, beam ellipse that I was talking about and Elena was talking about in the lectures. These ellipses have several parameters. Now, one of the parameters is the field of the ellipse, which is emittance. This is defined by the ion source, so we cannot really change it, but the rotation of the emittance can be changed. And this is basically rotation of the emittance is decided by two parameters, alpha and beta. So there are two parameters in one plane and two parameters in other plane, horizontal, vertical. So in total, we have 4 parameters. And if we want to change 4 parameters independently, we need, in principle, 4 quadruples. Now, with some, there are some relations between those parameters. So actually, 3 quadruples is enough. There are also ideas how to do it in a way let's say, yeah, basically the amount of quadruples is related to the amount of degrees of freedom you want to have when you tune your beam. Sometimes if you have really rigid design, you actually don't need any quadruples, but then you have to be really sure that all the elements on your beamline behave as you design, which is usually not case, and you would like to tune things. Yeah, sorry, it was a nice question, but a bit challenging to explain. I hope I did it well. It's to tune the beam. You need quadruples to tune the beam. Is CERN 750 megahertz RFQ only for carbon ions or other species? Basically, machines are designed for charge to mass ratio. So if we design RFQ for charge to mass ratio 1/2, like for helium 2+ or carbon 6+, and here there should be another question actually, then we can accelerate any ion, even uranium 92+ can be accelerated in the same machine. All right.
Mariusz, I'm afraid we will have to stop here with questions because we are running late. Thank you very much for answering. It's very much appreciated, of course. And
Nicholas,
yes.
Maybe I could make a comment on the connection to the CIST project, since I was involved from the beginning of shaping this project. I think the connection is the ambition for capacity building. Actually, this was the ambition of the sponsor, Eddie Offerman, who is funding this project in Sarajevo. And indeed, this is the commonality with the ambition of CIST. Now, if this hardware, this particular hardware is going to be exact hardware that is going to be used, or if Sarajevo is going to be a hub, etc., is to be seen, right? But certainly the people that are going to be trained there is exactly what was the aim of both projects. Okay, thank you.
Thank you for the clarification, Jota. We will now move on to our next speaker.